Hi friends, in this video we will discuss Gram-Schmidt process. Then we will cover the QR factorization of a matrix, and then we will cover what do you mean by inner product space. So first of all, the Gram-Schmidt process. Yes, this the Gram-Schmidt process actually it is an algorithm. Gram-Schmidt process is a algorithm or a method to find the orthogonal basis of a subspace, that is W, or it can also be used to find out the orthonormal basis. Orthonormal basis. So what is the difference between orthogonal basis and an orthonormal basis? Actually, you can if you have orthogonal basis, then you can derive orthonormal basis from that by normalizing this orthogonal basis, okay, by a process known as normalization. Okay, now so we will be discussing the algorithm to find out the orthogonal basis first, and then we will extend the discussion to orthonormal basis. Orthogonal, okay, first of all, what I mean by an orthogonal vector. Suppose we have u1 and u2 two vectors. We have, that is, some u1 is equal to some 2 3 1 and u2 equal to some 1 7 8 we have. So these are ortho for example, these are orthogonal vectors. Suppose if you just imagine like that, okay, that means u1 dot u2 will be u2 equal to 0. Suppose you imagine, but in this case it will not be equal to 0 first of all. Then okay, then I will just okay, this will be 0, then this is 0, and this is again, right. So these are orthogonal. These two are orthogonal vectors. Then what do you mean by an orthonormal vector? Then orthonormal vector means you have to actually u1 will be u1 is equal to, it is 2 3 0. Now u2 equal to 0 0 8. So u1 after orthonormal vectors means the orthogonal basis after normalization you will get orthonormal basis. That means normalization means you divide all the elements, all the entries of the vector by its magnitude, its norm, I will say. That means norm u1, okay, u1 by norm u1, okay, that is the normalized vector u1 dash. That means norm u1 means norm u1, we have the formula under root 2 square plus 3 square plus 0 square. That means under root 4 plus 9 plus 0, that's equal to the root 13. And normalization means you divide this norm u1, that is under root 13, okay, under root 13 by you divide the vector u1 by norm u1. That means 2 3 0, all these are 2 3 0, that is I'm representing it as a vector, that means as a matrix, that means is 2 3 and 0. So you divide this by its norm u1, that will be equal to 1 by root 13 into 2 3 and 0, that will be equal to 2 by root 13, then 3 by root 13 and 0. So this is the normalized vector. So orthogonal basis means uh, if these u1 u2 forms the orthogonal basis, then orthonormal basis will be then by normalizing this u1 and u2, you will get the orthonormal basis. So normalization process is this vector divided by norm of that vector, like your unit vector. Okay, so that is the orthogonal basis and orthonormal basis. So once you have orthogonal basis, then it is easy to get orthonormal basis, right? So we will discuss the orthogonal basis. Yes. Then this Gram-Schmidt process is used. It's used to find out the orthogonal basis or orthonormal basis for a subspace W. Now this is the process or the algorithm. This is the algorithm. How this algorithm is obtained, that we will show it by explaining two examples, and that means we will explain two examples, and those two examples will be extended to, or those two examples will be generalizing. We will generalize the method or the process or the algorithm for all for any dimension, equal to n. Okay. Yes. So let me consider the example 1. That is, it is given that two vectors x1 and x2, which belongs to x1 equal to and x2 equal to, so x1 will be is equal to 360,122. Okay, 360,360, and this is 122. So it is clear that this x1 and x2 vectors belongs to R3, our three-dimensional space. Three-dimensional space which is having like this, having x1, x2 and x3 coordinates. X1, x2, x3 coordinate system. This like this. This x1 and this is x2 and this is x3. So x1, x2 coordinate system. Now this x1 I'm what representing in this three-dimensional space, that means 360, that is x1 x2 x3 x3 0. X3 0 means, okay, let me consider in this manner, that is this is This is okay. This is x1 and this is x2. Let's say, right, and this is x3. No, it is not like that. X1, x2, and x3. Okay, let me consider like this, because we have to follow the notations of the textbook. Okay, so that it will be very easy to understand. So this is x1 and this is x2. This is x3. Okay, so x1 will be 360. That means x3 coordinate is 0. That means it will be on x1 x2 plane. So it will be like this, a point like this. This is x1 point, and the vector will be like this as shown. Yes, this is the vector, my x1 vector. Okay, this is my x1 vector. Now I have to x1 vector, and this, if you extend this to this line, we extend, right, we extend like this, then this will be the span of x1, span of x1, right? So this straight line passing to the origin, it will be span. It will be span of x1 like this. Now I have to mark x2, that is 1 2 2. 1 2 2 means that it will be somewhere in the 3D space, right? So it is like this. That is, this is x2. Okay, this is x2 point, and this is my x2 vector. Now I have this, yes, given x1 and x2, right? The examiner has given x1 and x2, two vectors like this, and they have also given w, a subspace w, which is equal to span of x1 x2. That means span of x1 x2 means some linear combination, all the possible, yes, all the possible linear combinations of x1 and x2, that is c1 x1 plus c2 x2. So all the possible linear combinations of x1 x2 constitute the subspace w. So that means this, yes, x1 is there, x2 is there, and so it will be, the w will be like this. W will be like this, the green line, and like this, containing the x2 point, containing the x1 as well as the x2 vectors, containing the x1 as well as the x2 vectors. That means these two lines, the line, straight line, that means the span of, we have span x2 will be a straight line, right? Straight line like this, straight line passing through the origin again. So the w will be the a plane, right? A plane containing these two straight lines, okay, extending from minus infinity to plus infinity. Okay, this is extending from like this. So it will be a plane, w plane. So w is the subspace. So you can, I hope that you can visualize that, right? Now, yes, now the examiner is asking you to find out or construct an orthogonal basis that is set v1 v2 orthogonal basis for w. That means orthogonal basis means v1 what are the conditions to have a basis. That means if this set s equal to v1 set v1 v2 is forms a basis. That means v1 v2 are linearly independent. That means c1 v1 plus c2 v2 equal to 0. This equation will only have a trivial solution, that is zero solution, that is c1 equal to 0 and c2 equal to 0. So that is the basis. And also span of v1 v2 should be equal to w. That means v1 v2 generates the w plane. So that is what I mean by basis. Then what do you mean by orthogonal basis? Orthogonal basis means another condition also has to be satisfied, that is this set v1 v2 should be linear, should be an orthogonal set. Orthogonal set means v1 inner product v2 will be equal to 0. That is they are orthogonal to each other. That's the another condition that has to be satisfied. So we will try to find out v1, find out two vectors v1 and v2 so that all these axioms are satisfied and thus form an orthogonal basis, right? So yes, so let me consider this procedure, that is the subspace w is shown in figure. Yes, the subspace w we have yes, we have this subspace w, yes, right, as shown in this figure 1, and also is shown in this figure also as w. Okay, right. Okay, now we have along with x1 x2 and the projection p. Yes, we are considering the projection p, which projection which is denoted by p of x2 vector. Okay, x2 vector onto x1 we are considering x2 vector onto x1. That means the component of yes that means p will be like this, that is x2, the projection of x2 onto the vector x1, that is in this figure 1 it is shown like this, and here we have yes projection like this. Yes, this is our projection p vector, the projection on x1. So let us say it is x1 here. So this is the projection p. So this point is p, and this point is x1. Okay, now I have this projection p, and also I will have another vector, that is the component of x2 orthogonal to x1, the component of x2 which is orthogonal to x1. That means this yes, this component of x2 which is orthogonal to x1 means this vector will looks like this. Looks like this. That means we have the other component of x2, that is here. That means this vector, some vector will be like this. So this vector will be this x2, okay, x2 minus p, okay, x2 minus p. So this x2 minus p and x1 sorry p yes, x2 minus p and x1 are orthogonal vectors, right? Now yes, which is in so these two vectors are in w. Why? Because that means this vector p, okay, and the vector x2 minus p, all these are in the subspace w. Why? Because this subspace w is Okay, subspace W is span of x1 and x2. That means all possible linear combination of x1 and x2. So this P is actually along the x1, right? P is along the x1. So that means P is some linear combination of x1, and this vector x2 minus P is also a linear combination of x1 and x2, because P is a linear combination of, or if you scale, or if you reduce the length of x1, then you will get P. So that means x2 minus some constant C is C1 into x1. Okay, that means the entire combination is a linear combination. So so it will be in W, because span of x1 x2 is W, right? So this vector is a span of x1 x2, and this vector is again a span of x1 x2. So these two vectors are in W, subspace W. Okay, now I have to find, my aim is to find out the orthogonal basis. Okay, orthogonal basis set v1 v2. Now I'm letting that we have two vectors, right? X1, we have two vectors x1, and we have x2 minus p, two vectors which are orthogonal to each other, which are orthogonal sets. Okay, and also they form the basis, they span W, right? They form the basis for the W. So we will equate this v1 and v2, which satisfies we will equate this x1 and x2 minus p, which satisfies all the axioms for an orthogonal basis. So we will have this v1 equal to x1 and v2 equal to x2 minus p, right? So then that means this v1 we have find out, and v2 will be x2 minus p, that is x2 minus projection p. Projection p formula will be what? X2 dot x1 divided by x1 dot x1 into x1. That is this is nothing but the projection formula. Okay, projection formula. Now we will get this v2 as 0, 0, 2. So finally we got v1 equal to x1, that is nothing but 3, 6, 0, and another v2, I have another vector got as 0, 0, 2, and these set of v1 v2, that is set v1 v2, forms the orthogonal basis. These are non-zero vectors which forms the orthogonal basis. So we have calculated or derived the orthogonal basis for W by a unique procedure, or a unique process, or in a unique manner. Okay, that means I have let v1 equal to x1, the first vector which is given, and I have calculated the next vector v2 as x2 minus p by calculating this projection, and x2 I have my yes negotiated with this p, and I got v2. So v1 v2 I got. Now this can be, this procedure or this method, okay, of finding two vectors that forms the orthogonal basis for the W can be extended to any number of ordinates, any number of dimension, for any dimension. That means for dimension equal to n, we have this kind of method. That means, that is what I mean by Gram-Schmidt process. The Gram-Schmidt have generalized this, that is v1 equal to x1 and v2 equal to x2 minus this x2 minus the projection x2 minus, that is projection of x2 onto the W, onto the subspace W, right? W, and v2 will be like this. So v1 and v2, these equations are true for for a for for a dimension equal to 3, for a dimension equal to not 3, a dimension equal to 2, sorry, dimension equal to 3 again. Yes, right, for dimension equal to 3, and we have find out two orthogonal basis set. Now this can be extended to any any subspace W of Rn. So the formula is like this. We will find out V1, and then V2 we will find out using this formula, and V3 we will find out as V3 equal to x3 minus x3 dot V1 divided by 1 dot V1 into V1 minus x3 dot V2 divided by V2 dot V2 into V2. That means the projection of x3, the projection of x3 onto a subspace W1, and this is projection of the same x3 onto another subspace W2, right? So this is the Gram-Schmidt process, and yes, this the same the previous discussion. The previous discussion can be extended. The discussion, the concept, the procedure can be extended to this example too. So by explaining this example too, we can generalize the Gram-Schmidt process. That means they have given three vectors, right? X1, x2 and x3 vectors, which all belongs to R4, right? Then the examiner is asking you to find out the orthogonal basis, orthogonal basis for the subspace W of R4, right? Now, yes, then what will be our proceeding? The first step is that that means our objective is to find out V1, V2, V3. Set V1, V2, V3 that forms the orthogonal basis for W of R4. So we will have step 1, that is we will assume that V1, the first vector V1 is x1, and W1 will be equal to span of x1, that's equal to span of V1, and then we will let V2, the second vector V2, be the vector be the vector produced by subtracting from x2 and its projection, the projection of x2 onto subspace W1, that is which is this the previous subspace which is spanned by x1 or spanned by V1. So that the formula of this V2 will be like this: V2 equal to x2 minus projection of x2 onto the subspace W1, right? So we will get this V2, V2 equal to minus 3 by 4, 1 by 4, 1 by 4, 1 by 4. And to have to reduce the complexity, I am multiplying this with 4 into this V2, and that's equal to V2 dash. I'm considering. So that means you will get V2 dash as this minus 3, 1, 1, 1. Right? Yes. And also we will get first we have considered a subspace W1 which is spanned by x1 or V1. Then now we will consider both we will consider another subspace, the new subspace, that is W2, which is spanned by the already given orthogonal vectors, that is V1, V2, or already calculated orthogonal vectors V1, V2. V1, V2, and in the step 3 we will we will let the uh, third element, third member of the orthogonal basis, that is V3, that is equal to uh, x3 we have, and x3, this x3 3 minus projection of x3 onto w2. So right, and then uh, before that we will calculate the projection of x3 onto w2 like this. Okay, yes, so that means, yes, in this manner we will calculate v1, v2 dash, and v3. Okay, actually it is v1, v2, and v3, but v2 got transformed into v2 dash by scaling it. So it doesn't matter if you scale a vector, its orthogonality will not change. So it again forms the basis, right? So v1, v2, v3 forms the orthogonal basis. Okay, so this is the now this is the summary of what we have done. That means we have find out, first of all we have w1 subspace, then we have, which is equal to a span of x1 or span of v1. Then we have, that means this is a straight line. Okay, this is w1. Then we have calculated this v2, which is orthogonal. Yes, this v2 is orthogonal. V2 means v2 dash itself, right? V2 means v2 dash itself. So this v1 and v2 are orthogonal to each other, that is 90 degree to each other. And then we have we have the subspace w2, and this subspace w2 contains both v1 and v2 dash, that is w2 equal to span of v1 and v2 dash, that is all possible combinations of v1 and v2 dash. Then you will get the w2 subspace, and then we will calculate v3, right? v3 similarly v3 will be equal to, again, the uh, the mm, the the vector we are considering is x3, and x3 minus the projection of x3 onto w2. That means, yes, like this. So x3, this vector x3, and this is the vector is minusing is this vector, that is projection of x3 onto w2, and these two vectors, when minus is put in between this, then you will get the vector v3, and this vector v3, okay, vector v3 and vector v2 dash or v2, and this v1, okay, this v1 vector, all these vectors are orthogonal to each other, because v1 and v2 uh, or v2 dash vectors are in w2 plane, and this v3 vector is perpendicular to this w2 plane. So v3, v2 dash, and v1 all are orthogonal or perpendicular to each other, and also they span, okay, they span what, w, the subspace w, which is equal to span x1, x2, and x3, right? And also this v1, v2 dash, and v3, or v1, v2, v3 are orthogonal set, right? So now, yes, now when we have proved, we have calculated the orthogonal basis for R3, for a subspace in R3 in example 1, and in example 2 we have calculated the orthogonal basis for a subspace W which is in R4, right? by a unique way of or unique method or unique algorithm. Okay, and that algorithm is known as Gram-Schmidt process, and that Gram-Schmidt process for finding an orthogonal basis for a subspace W which belongs to Rn is given by this theorem number 11, right? So that means you can generalize it. Okay, you can generalize from example 1 and example 2 to this dimension n. Yes. So then I will give you so many exercises based on Gram-Schmidt process and also previous concepts. Uh, okay, you solve those problems and we will consider it as assignment. So that we will do. Okay. Now, yes. Now the next topic, important topic, that is QR factorization of matrices. A matrix consider a matrix A which is of the order m by n, and A is equal to, let A is equal to matrix, sorry, this matrix, this A1, A2, A3, etc. AP, where A1, A2, A3, AP all are vectors. Vectors belongs to Rm. A is a matrix of order m by n. That means m number of rows will be there. Okay, and n number of columns will be there. So A1, A2, A3, etc. AP all are vectors belongs to Rm. So because m number of entries will be there, because number of rows equal to m. That is right. Now A1, A2, A3, etc. Yes. Now suppose A1, A2, A3, etc. AP are linearly independent. Independent vectors. A1, A2, A3, etc. AP are linearly independent vectors. That means the column vectors of A are linearly independent vectors. Linearly independent vectors you know, so I'm not repeating that. So if A is an n by n matrix with a linearly independent columns, then A can be factored. That means suppose we have a number like 30, we have 30 is a real number we have, and this 30 can be factorized as 5 into 6, right, or 6 into 5 you can, right, or it is equal to again 10 into 3, right, you can factorize this 30. Okay, similarly we can factorize this matrix A also. A equal to Q into R. This is known as the QR factorization, where Q is m by n matrix whose columns form an orthonormal basis. Orthonormal basis. Whose, yes, orthonormal basis for column space A, and R is an n by n upper triangular invertible matrix with positive entries on its diagonal. Yes, this is the QR factorization method. Now we will explain this QR factorization of matrices with an example. Okay. Now orthonormal basis means we have if you have orthogonal basis, then you normalize it. That means we have orthogonal basis v1, set v1, v2, v3. Then orthonormal basis will be obtained as by normalizing these vectors. That is v1 by norm v1, that's equal to v1 dash, and v2 by norm v2, that will be equal to v2 dash, and v3 dash will be equal to v3 by norm v3. So the set v1 dash, v2 dash, and v3 dash will form the orthonormal basis. Right. Now that means this Q, the peculiarity of this Q matrix is such that it is of order n by n, okay, and its columns are form the orthonormal basis for the column space A. Orthonormal basis for column space A. And okay, right. Now this is the definition, so we will explain with the example. Suppose we have the vector A, which is okay, which is formed by x1, x2, and x3 in example 2. That means yes, this is x1, this is x1, this is x2, and this is x3. Right. That means we have seen in example 2 that this x1, x2, x3 are linearly independent vectors in R4. Okay, that we have seen in example 2. So the first condition is satisfied for QR factorization. Right. Now that means A can be written, or A can be factorized as A equal to Q into R. Then the next question is, what is Q and what is R? Now what is Q? What is Q means? Q is nothing but our it is in theorem 12 it states that the column vectors of the Q forms the orthonormal basis for column spacing. That means by Gram-Schmidt process you can find out the orthonormal basis for column space A. Okay, column space A means it is nothing but call A that is equal to span of x1, x2, x3, and which is equal to our W, subspace W, the subspace in example 2. Right. So what then yes, in example 2 we have we found the orthogonal basis, and you normalize it. Okay, you normalize this orthogonal basis, that is v1, v2 dash, and v3. Normalize it. Okay, that means v1 by norm v1, v2 dash by norm v2 dash, v3 by norm v3. Okay, that means you will get this 1, 2, 3, 4. Yes, this you will get the orthonormal basis. Right. That means that you write as the columns of Q. The columns of Q is exactly that. That means Q is equal to 1 by 2, 1 by 2, 1 by 2, 1 by 2. Yes, this matrix. So you got Q, right? Now you have to find out R. A is equal to, so that you can write A is equal to QR. Now we have A is given, Q we calculated Q. Now you have to find out R. That means you have this identity we have. That means Q transpose, okay, into A, that is equal to Q transpose into Q R. That means I am pre-multiplying this equation by Q transpose. That means Q transpose into A equal to Q transpose into QR. Okay, that means Q transpose into A equal to Q transpose into Q into R. That means Q transpose is Q. Q transpose Q means it is nothing but the inner product, right? Because Q is some V1 dash, V2 dash, and V3 dash, and Q transpose means column vector V1 dash, V2 dash, and V3 dash. So if you multiply this, that means this is nothing but your inner product. Your it's inner product or dot product. That means dot product of orthonormal vectors will be unity 1. That means we get since it is matrix multiplication, we will get the identity matrix I. Okay, so that means Q transpose into A equal to, on RHS we have identity matrix I into R, that is equal to R. So R, we got the formula for R. R is equal to Q transpose into A. That means you take the transpose of the Q matrix and multiply with A, then you will get R. Okay, that is the SQR factorization. Okay, so that is also done. Now we have the definition of inner product space we have. Okay, we will discuss. Yes. Okay, the next important topic of module 2 is inner product spaces. Definition of inner product space is like this. An inner product on a vector space B, that means we have a vector space B. An inner product on a vector space B is a function. Okay, inner product is a function. So each pair of vectors u and v in B, that means we have two vectors u and v which belongs to the vector space B, and u inner product v means we are assigning, it is a function that assigns this inner product to a real number, some real number R, or some real number C. Okay, real number C. And if this inner product, and the inner product is written as like this, is the symbol for inner product, that is inner product u comma v. This is the symbol. And if it satisfies the following axioms, that is inner product uv equal to inner product u, and inner product u plus vw comma w equal to inner product u comma w plus inner product vw, and these and the rest of the axioms, that means total of 4 axioms. Okay, if that the inner product satisfies these axioms, then such kind of a vector space with this inner product is called as inner product space. Okay, that's the definition of inner product. Right, now yes, we will explain. So we will get a clarity with this example, that is example 1. Fix any two positive numbers, say 4 and 5, and for vectors u equal to u1 u2 and v equal to v1 v2 in R2, That means this is ordered pair u1 u2. This is ordered pair v1 v2, which belongs to the two-dimensional, that is x1 x2 axis, and set inner product u equal to, it is like this, 4 u1 v1 plus 5 u2 v2. So this is the examiner uh, define the inner product uv as equal to this relation, 4 u1 v1 plus 5 u2 v2. This is the expression. Then the examiner is asking you to show that equation 1 defines an inner product space, right? So if this equation 1 has to define as an inner product space, then it has to satisfy the these four axes, right? So we will check it out one by one. That is inner product uv equal to inner product vu. First axiom will be satisfied very comfortably. That means inner product uv is defined as 4 u1 v1 plus 5 u2 v2, okay, which is given by the examiner. Then inner product vu will be actually you can u1 into v1 will be the same as v1 into u1 because multiplication. All right. So in for v1 that will be equal to this 4 v1 u1 plus 5 v2 u2, that is equal to inner product v. So first axiom is satisfied. Then the next axiom is we are defining another vector w in that vector space R2, and this w is equal to ordered pair w1 w2. Now we are checking for the second axiom, that is inner product u plus b w should is equal to u plus inner product u plus b comma w is equal to, it is 4 into u1 v1 plus, yes, by definition this will be the RHS, and you open all those brackets and rearrange, then you will get u inner product uw plus inner product vw. So the second axiom is also satisfied, right? Yes. And then inner product cu comma v equal to c, you can take it out, and inner product u. So this is also can be proved to be satisfied. So also 4 also can be easily proved. So our conclusion is that the inner product defined by the examiner, this given by this the equation 1, forms the inner product space. Okay, so that is the entire discussion is all about over, right? Thank you.